Let's get started on the second session. This session we're going to have three presentations that go into a bit more detail about some of the specifics of the 31814 reorganization. And as I mentioned in some of the questions and answers at the end of the last session, one of the things that's been has been added as technical changes are chapters on structural systems and on diaphragms. Jack Moehle, who is the currently on the code, and Chair Sub H that committee was responsible for moving those chapters into the code. He is also the chair-elect for the next 318 code cycle. So Jack, let you start the presentation.
Thank you, Randy, and welcome to all of you to the second of the Concrete in the Americas sessions dealing with the ACI 318 2014 building code. It was a great challenge and also a great experience working with the 318 committee on this new edition of the code. I have never seen a group of engineers and building officials and others in a committee work so hard, so diligently to do so much. And I firmly believe that what's been accomplished is really going to be in the interest of new students, engineers, and the public safety. So I'm looking forward to this new code coming out. I will be talking mainly about two new chapters that appear in the new code. These are a chapter on structural systems and diaphragms. To get a sense of sort of where things go, I'd just like to remind the conceptual design of the code, which has been talked about before. The whole idea of the code is to organize it by what you're designing. There's a structural system, there's slabs and beams, there's columns, walls, diaphragms, and other things that should be part of this building that's being designed. And then there's some general requirements for analysis, strength, serviceability, construction, and so forth. And so the code is organized around this conceptual design. And the various chapters, you know, I like to think about how the code is broken into its parts. And so I look at, there's a general section up front, the analysis comes next, member design, joints, connections, and anchoring to concrete, seismic design, materials and durability, and so forth on down the road. And there's 27 chapters that fit into this. And among these 27 chapters are the two new chapters. In Chapter 4 on structural systems fits up with the general material. In a sense, it's a general statement of what's required for the design of a building. It also serves as a roadmap to what's going to come in other chapters of the code and pointers to all those different parts of the building code. And having a roadmap of this type is important because the code is reorganized this time. It's so different from how it was organized in the past. Having a roadmap in this Chapter 4 to where you're supposed to go to find the different pieces and what you're supposed to do is, I think, really important. And then one of the members that has always been missing from the main body of the code is diaphragms. And we've talked about diaphragms in the seismic chapter where they become very important for developing your structural system, but have never had explicit provisions within the main body of the code covering diaphragm design. Well, as the code gets reorganized and now we have members up front, there was a hole identified in the structure of the code. One of the main members that we have to have in every building is a diaphragm, or many diaphragms. And there was no chapter on diaphragms. And so the challenge was, well, can we, while we're reorganizing this code, come up with a chapter on diaphragms that's general enough and has some specific useful requirements so that it fits into the structure of the whole code. So let's take a look at what's in these two chapters. We're not going to go into a lot of detail with them. The structural system chapter, Chapter 4, basically says every building has to have a structural system. that is configured in a way that will resist the applied loads and will provide a load path from points of application to points of resistance, period. And so the chapter says, okay, there are loads that are going to have to be resisted by this structural system. The chapter identifies what are the different loads that have to be resisted, where in the building code, chapters 5, it turns out, do you find the loads, and what kinds of analyses are acceptable for figuring out the load paths and analyzing the required strengths. So chapter 6. The systems chapter that identifies that if you have slabs, go to chapter 8 and 7. If you have beams, chapter 9. Columns, 10. Walls, 11. Diaphragms, 12. What could be next? Foundations, 13. And then joints and connections are slipped in 15, 16, and 17. And then last is seismic systems. And the chapter on structural systems doesn't say you have to have all these things, but this code is built around the notion that a structural system is made up of these kinds of elements. And if you use these elements to provide a load path within the building, these are the places you have to go to find the various provisions. For the seismic force resisting system, there is a little extra discussion about where you have to go within the building code to find the requirements. It's noted that every structure must be assigned to a seismic design category anywhere that this code is used. The general building code defines what's acceptable for seismic force resisting systems. If you are assigned to a seismic design category A, you need comply only with all the other chapters of the code, but not the seismic chapter. If your building is assigned to seismic design category B through F, you have to satisfy certain provisions in chapter 18. So again, it's a pointer to where you have to go with regard to seismic. The design method that's assumed in this code is outlined in the last few sections of this chapter. It's really an LRFD design basis, so there's a strength requirement. The general statement is that the demand has to be less than the reliable strength, or a phi times a nominal strength. In a limit state design, there's also the requirement to check serviceability. The statement in this chapter is quite simple. Go to the various member chapters to find member-specific requirements for serviceability. For example, for beams, go to the beams chapter where you'll find requirements on distribution of reinforcement and the like. But then also go to chapter 24, which contains other requirements for serviceability, such as deflection limits. Durability requirements, there are pointers to chapters 19 and 20. With regard to sustainability, it's noted that the engineer of record is allowed to introduce requirements for sustainability, but those requirements shall not override the requirements for strength, serviceability, and durability of a structure. I think very importantly, this chapter identifies that structural integrity provisions exist in this code, and they have to be adhered to. And it points to the various member chapters to find where those provisions are. I'm still finding engineers who don't realize that there's structural integrity provisions hidden away somewhere in Chapter 7 of the Building Code. Well, this is up front now, a pointer to where this is. And then fire resistance, mainly to be in accordance with the general Building Code. Now, there is, among the many chapters that the structural systems chapter points to. One of them is the new chapter on diaphragms and collectors. And so a diaphragm is an element that resists forces within its plane in general. So maybe there's a roof diaphragm, many floor diaphragms, etc. A collector is an element that transfers shear forces from the diaphragm into the vertical elements of the lateral force resisting system. So there are collectors that may occur in elevated levels where you're picking up diaphragm forces and delivering them to the lateral force resisting system. And then there are collectors, or might be called distributors, that take force out of those vertical elements and transfer them into other diaphragm elements. The diaphragm chapter is set up just like all the other member chapters. Has all the same headings, but the requirements are here specific to the diaphragm. The first part of this chapter introduces the scope and notes that this chapter covers cast-in-place diaphragms, precast diaphragms with cast-in-place topping slab, precast elements with end strips, and then interconnected precast elements without cast-in-place toppings. So those are the types that are specifically covered within the chapter. Today we'll just look at mainly the cast-in-place diaphragms that I think are the most common that most of us run into. The chapter also notes that the scope includes all types of loadings. It's not just seismic loadings anymore, but gravity loads, wind loads, seismic loads, etc. are covered by this chapter. Back to the picture of a simple diagram of a building. The roles of the diaphragm are spelled out in part in the code and in part, because this is a new chapter, through some illustrations in the commentary. The first role of the diaphragm, of course, is to tie all the elements of the building together so that, as an example, the vertical elements of the lateral system and of the vertical framing system need bracing out of their planes to support them. We need to tie various elements together to create a three-dimensional system that's fairly rigid. So that's the main first role that a diaphragm plays. Second role is the resistance of out-of-plane wind pressures or internal inertial loads that may arise from earthquake loading. Third kind of load and role that the diaphragm plays is to pick up below-grade soil pressures. So any building that has subterranean levels is liable to have soil pressure that has to be dealt with. And in this instance, the external basement walls pick up this pressure, generally transfer it vertically out of plane to diaphragm elements that are in the foundation or at subterranean levels or at grade level. And then those elements transfer these lateral forces either to basement walls that are in plane or other internal elements that resist those soil forces. There are thrusts that arise when vertical elements of the system are inclined. So this is identified. And then there are transfer forces. Whenever a structural system changes in its plan dimensions and there are lateral forces applied especially, there's transfer from one line of framing into another line of framing. So these forces are identified and have to be taken care of. Stiffness assumptions. We started out trying to rationalize our own set of stiffness assumptions. That didn't go over well in the balloting process. We tried to adopt the ASCE 7 provisions for aspect ratio for seismic design. It turned out that didn't go over so well because it turns out in ASCE 7, in the wind design provisions, there's different aspect ratios. So we tried those, and that didn't go over so well with the seismic folks. So in the end, we ended up adopting a very well-known provision within the building code. Any set of reasonable and consistent assumptions are permitted. And this passed instantly. Now, most diaphragms are modeled as rigid in their plane, and this is generally permitted as part of the code. But we do point out, this chapter does point out, that there are instances where flexibility in the diaphragm should be considered, mainly in the commentary in this case. It was also important in some aspects of the diaphragm consideration to to note that if the rigid diaphragm assumption is assumed, then if there is eccentricity between the lateral forces and the centroid of resistance in one direction, it's acceptable to use transverse elements to resist that eccentricity. Now, strength in a diaphragm can be determined in many different ways, and there are many different practices around the world in how loads are considered and how they're resisted. And so the chapter is written in a way that permits any reasonable set of assumptions that satisfies equilibrium. And so there's a beam model, a very common model that's used in practice. This chapter is kind of written mainly around that idea. But the chapter also recognizes that strut and tie modeling is permitted in accordance with chapter 23, which covers that topic. Finite element models can be used, in which case chapter 22, which provides all the section strengths, can be used to determine whether the strengths provided are adequate. And last but not least, any alternative method that satisfies equilibrium and that provides required strength for all elements in the load path, those methods are also permitted. And there are many practices that really fall into this latter category that couldn't be codified here. The basic beam model, many of you are probably familiar with, but maybe some are not. The idea here is that the diaphragm is idealized as a beam spanning between vertical elements of the, in this case, lateral force resisting system. So there's the beam model. Beam develops shears and moments like any other beam. The usual way of approaching the flexural strength, or the moment strength actually, for this case is to resist that moment by a tension and compression couple, preferred to be at the extreme edges of the diaphragm, which is explained in the commentary. And if you're resisting the moment with concentrated chord forces, as shown here, then equilibrium requires that the shear stresses be distributed uniformly through the thickness of the diaphragm. So as for design, if you take this approach, which is very common for the design of diaphragms, then the design of the tension and compression elements really follows the traditional approach for members in compression and in tension. This is laid out, and there's reference to, I think it's chapter 22 or 3, where all the strength methods are. If you have this uniform shear transferred across the thickness of the diaphragm, the shear strength for the diaphragm then is defined in fairly familiar ways, as shown here. So this determines shear reinforcement that would be parallel to the shear. If there is shear stress that is applied uniformly through the thickness of the, or the depth of the diaphragm, then collectors are required to pick up those shear stresses and to transfer them from the diaphragm and into the vertical elements of the lateral force resisting system. So as suggested here, if there's a shear on the diaphragm from A to D, that's going to load up one of the collectors, AB, in compression. The collector along CD gets loaded up in tension, and those forces have to be then transferred out of the collector and into the wall along the wall length, either the entire length or some suitable length that's selected for design. It also is quite acceptable and common to spread the collectors out into a diaphragm or to have them entirely in the diaphragm, in which case that design also is discussed within the chapter. And then if the diaphragm is distributed, as shown here, then we might end up with the collector reinforcement as shown here, distributed out transversely into the slab, picking up the slab or the diaphragm forces. The transfer then into a structural wall could occur through dowels that are provided for shear friction resistance. And so this basic approach and the design equations for this are referenced within the chapter. Only one slide on pre-stressed and precast diaphragms, so we can finish in a reasonable time. There's a lot of detail if you get into these different systems. And We're not going to go into them, but I would like to note that if you have a pre-stressed or pre-cast diaphragm, moment can be resisted directly by the pre-stress that exists in the diaphragm. It can be resisted by mechanical connectors. And shear can be resisted by topping slabs or topping slabs composite with precast elements. It can be resisted by shear friction at joints. And in fact, if you have precast elements that has a topping slab, then you really have to consider shear friction through the thickness of the topping as the way to resist shear between the different elements. And then mechanical connectors also are permitted. So again, just summarizing what this presentation addressed, it was looking at the structural system requirements that are added in Chapter 4, serves as a roadmap to all the other chapters. Make sure that you know where you're supposed to go and what loads to consider. And then the new chapter, Chapter 12 on diaphragms, is ready to go. And I hope this has been helpful for understanding these two new chapters in the code. Thank you.
Okay, thank you, Terry. The next presentation is going to be getting into the details of member-based design in a much more specific way than what we've been talking in generalities. Originally, this was going to be done by Robert Frosch, as is somewhat become the case within the ACI 318. We fall to our DH, designated hitter, and our designated hitter for this task is Ken Bondy, and we really do appreciate him on short notice being able to give this presentation. Ken, thank you.
Thank you, Randy. I was a little surprised and disappointed that two of the previous speakers, Larry Novak and Alan Balmer, revealed the year of their birth. For some of us, that was a little depressing. So I'm going to say right up front that I'm not going to do that. So sorry. My talk will focus on the member-based design issues in ACI 318.14. If you look at the current version of the code, the 2011 edition of ACI 318, you'll see that it's a mixed format, and that format has been unchanged since 1971, 42 years. It's a mixture of behavior-based requirements. For example, Chapter 10 addresses flexure and axial loads. Chapter 11 addresses shear and torsion. But there's also some member-based chapters. Chapter 13 exclusively addresses two-way slabs. Chapter 14 addresses walls. Chapter 15 addresses footings. And as others have pointed out, that results in a code that has the requirements for any one given member in a whole bunch of different places. And there's not easy pointers to tell the user of the code where to go to get all those requirements. This turned out to be a really popular slide. I'm actually kind of glad that there were one or two presentations where it didn't appear. But in any event, for example, if you were designing a column and a joint, the way I've done it is a little animated, but you would find the axial load and shear capacities in chapters 10 and 11. You'd find the strength reduction factors, the phi factors, in chapter 9. If you needed to know the cover to the ties and reinforcement, you'd find that in chapter 7. You'd also find the minimum quantity of ties and spacings in chapter 7, different section. For lap splices, you'd have to go to chapter 12. For the ties that are required in the joint, you'd have to go back to chapter 11. If you wanted to know the maximum slope of the vertical bars, you'd have to go again back to chapter 7. So you need 5 chapters for one design detail, and there are not easy pointers to those. There's no tabulated list that tells the designer to do all these things. You just have to know it. When we decided to reorganize the code, 6 years ago, we had a series of goals. The first one was to ensure that all code requirements for each member type are really easy to find. We wanted to provide explicit, specific detailing requirements for each type of member. We wanted to provide what we felt was a clear design path, the way a structural designer would normally approach the design of any given member. And we wanted to make it easier to introduce new topics. Now, when new research comes out, new information that we feel should be in the code that's important for the profession, because of the mixed format in the last 40 years, it's a little difficult to determine where to put that information. I believe it will become much easier to include new information in the future. And of course, overall, we wanted the code to be user-friendly. The philosophy that we adopted to accomplish those goals is the following. The code will be member-based. All the requirements for each member design are in one chapter. And we guarantee you, the user of the code, that if all the requirements for a particular member contained in one chapter are satisfied, you're done. The design is complete. The original intent was that there would be no substantive technical changes from the current version of the code, and certainly all the current ACI 318.11 requirements are incorporated, but there have, of necessity in the last 6 years, there have been some technical changes that have been made, and those will be highlighted. One interesting thing that came up in the development of the reorganized code is a duplication. There are some general items in code issues and requirements that apply to all types of members, or at least to more than one type of member. And that would include concrete and reinforcing steel properties, load factors, fee factors. Different analysis methods can apply to various members, and of course serviceability requirements can be extended to a variety of different members. We had a bunch of discussion about repeating these provisions in each member chapter. In other words, we're going to do a member-based code, so let's stick to it. Let's even if we have to duplicate things, let's duplicate. Let's say everything in writing in each chapter. We're a little concerned that the code might be 2,000 or 3,000 pages long if we did that, and we looked at this type of thing. This is a chart that we've seen before, but in the current format, you can see that the 1971 code had 174 pages. 318.11 has 503 pages, so it's almost tripled in size up to the 2,500 requirements. So the decision was pretty easy. Before I leave this slide, it's kind of interesting that this is a little bit of an aside, but the 1910, the very first edition of the ACI building code has been discussed today. It had a mighty total of 14 pages. One interesting thing, if you ever get a chance to look at it, do. You can read it in a half hour, unlike the current code. One interesting thing that you'll find if you read the code is that the very first version of the ACI code was strength-based. It was based on an ultimate strength method. It defined the capacity of the member as a tension compression couple internally. So the very first ACI code was strength-based. In the next 60 years, that kind of got lost and then refound up to 1971. So there's a little interesting aside. The decision was easy. For the general issues and procedures that typically apply to all the member types, or to more than just one type, we're just going to specify it once. We'll use a separate chapter and refer to that requirement or that chapter. We'll point to those requirements within the member chapters. So within the member chapters, if you get to a point where you have to go to another chapter, there's a pointer, very clear pointer to the section that's required. Once you accomplish that section, in a different chapter, you bounce right back to where you were in the member chapter. And we believe that that's reasonably coherent, and it means that you won't need a forklift to pick up the code. I like to think that the code is organized in 10 parts. Again, you've heard this before. The first part is administrative. I really like Chapter 4. That's the chapter that Jack discussed, the structural system requirements. It's largely new. It's a roadmap to everything that goes on in the code, and it's very important. We have 2 chapters on analysis, loads and load combinations, and structural analysis methods. The heart of the code are the 8 member chapters in Part 3. The members that are addressed by the code are one-way slabs, two-way slabs, beams, columns, walls, diaphragms and collectors, foundations, and plain concrete members. Part 4 of the code addresses beam column and slab column joints. It addresses connections between the members, and it addresses anchoring to concrete, which is the old Appendix D. Part 5 is a chapter on seismic design. That's substantially the same as Chapter 21 of the code. Part 6 addresses materials and durability. Chapter 19 addresses concrete properties. Chapter 20 addresses steel properties. The 7th part addresses strength and serviceability, strength reduction factors, fee factors. Chapter 22 addresses sectional strength, the unified design method. Chapter 23 brings the old Appendix A into the code, strut and tie methods. Chapter 24 addresses serviceability. Part 8 addresses general reinforcement details. It's largely equivalent to Chapter 12 in the 2011 code. Terry addressed Chapter 26. I feel it's an extremely important chapter. There were construction requirements scattered all throughout the code, the 2011 code, and these are based on a requirement in the general building code in IBC. These construction requirements were required to be incorporated into the construction documents by the licensed design professional as applicable. In other words, the code is written to the licensed design professional. The contractor satisfies the code not directly, but by conforming to contract documents. The contractor has a right to presume that the construction documents that he's working from contain all applicable code requirements. So what we've done in Chapter 26, largely haven't changed things. There's a difference of opinion on that. I believe those responsibility issues have always been there. Nonetheless, we've sure made it easier for the design professional because we've collected all of those construction requirements and put them in one place in Chapter 26. And the last chapter of the code is Chapter 27. It's the old Chapter 20, the load test structure and strength evaluation of existing structures. I think one of the best features of the reorganized code is in the member chapters. They're all organized exactly the same way. They all have 7 identical sections. They're not identical, but the headings are identical. And we tried to make it the flow of what a designer does in the design of a member. I'll talk about these specifically a little later, but they include member section 1, M.1, a scope section, M.2, a general section, M.3, any design limits, M.4 addresses the demand on the member, the required strength, M.5 addresses the nominal strength, the capacity, M.6 addresses the minimum reinforcement, and M.7 addresses any unique detailing requirements for that member. And I think it's really valuable and really important to know that each of the 8 member chapters is organized exactly this way, exactly in the same way. The scope section, M.1, tells you what's included in the chapter. The applicability, non-pre-stress, is the member applicable to non-pre-stressed concrete, pre-stressed concrete, cast in place, precast. There's a general section that addresses materials, connections to adjacent members, and any stability requirements such as bracing. M.3 addresses any design limits that apply to this particular member. Could be dimensions. The depth of the member has to be less than or equal to some value. Deflection limitations, any limitations on the steel strain, and any service load stress limits that apply. Endpoint 4 addresses the demand, the required strength, discusses the calculation of factored forces, moment shear, torsion, and axial, and then the critical locations where those forces must be addressed in the member. The moments, for example, must be calculated at the face of the support, the shear at some distance away from the support. Endpoint 5, the nominal strength section that addresses the capacity of the member, and for the 4 types of loading and forces, moment, shear, torsion, and axial load, fairly straightforward that the nominal capacity multiplied by the phi factor has to be greater than or equal to the demand. Endpoint 6 addresses any requirements for minimum reinforcement in the member. For example, there could be a requirement for minimum flexural reinforcement. We're familiar with this equation for A sub S. There could be requirements for minimum shear reinforcement, and those will all be collected and contained in one section, endpoint 6. Endpoint 7 addresses any detailing requirements that are important for that member. Generally, this would be maximum spacing of reinforcement for either crack control or for shear reinforcement. For example, I've shown the requirements for shear reinforcement from the present Chapter 11, 11.45, which divides the beam type into non-pre-stressed beams, pre-stressed beams. For each one of those beams, you have to consider the shear strength that's resisted by the shear reinforcement, and for each of those, and that's a function of whether it's less than or greater than 4 times the square root of F prime CBD, and then there's a maximum spacing requirement for each one of those. So all of that, any detailing requirements are all contained in section M.7, in the 7th section in each member chapter. So again, I'm a little bit like a broken record. The benefits are that the complete design for each member type is contained in one chapter. All the requirements are in one place, either in a complete, unique written requirement or a pointer to a general chapter somewhere else in the code, from which you return to the member chapter. The member chapters are all organized exactly the same in 7 sections. The code is unified. Non-pre-stressed and pre-stressed members are included in each member chapter. There's no separate place that you go to see what you need to do for a pre-stressed member. And we believe the code has been substantially simplified, particularly by the use of tables. One example of this, very important code section 10.2.7.3, where the beta 1 factor is described. That's the relationship between the depth of the rectangular compression block A in flexural analysis and the depth from the compression fiber to the neutral axis C. In words, and I kind of like to read them because this is a modest tongue twister. There are a lot of other sections in the code that are tougher than this, but for F prime C between 2,500 and 4,000 psi, beta 1 shall be taken as 0.85. For F prime C above 4,000 psi, beta 1 shall be reduced linearly at a rate of 0.05 for each 1,000 psi of strength in excess of 4,000 psi, but beta 1 shall not be taken less than 0.65. That is all beautifully tabulated in one table that I think is much clearer. The leftmost column addresses the concrete strength that you have, and then for each one of those concrete strengths or ranges of concrete strength, beta 1 is defined very succinctly in the right column. I think it's much easier, much clearer to do this in a table. We've also made liberal use of figures. That same relationship can be shown very clearly in a very simple figure that I think is much easier to visualize and understand than all of those words. The classic, and this is kind of the icon tongue twister in the 2011 version of the code, there's no better example for this simplification than this one. If you were a designer in the current edition of the code, the 2011 edition of the code, and you were designing a pretension member and you wanted to know what the minimum spacing was for the pretensioning tendons, at the ends of the member, you'd have to go to section 7.6.7.1, and it's kind of fun to read it. Let's do it. The center-to-center spacing of pretensioning tendons at each end of a member shall be not less than 4 bar diameters for strands or 5 bar diameters for wire, except that if specified compressive strength of concrete at time of initial pre-stress, gasp, F prime CI is 4,000 psi or more. Minimum center-to-center spacing of strands shall be 1 3/4 inches for strands of 1/2 inch nominal diameter or smaller, and 2 inches for strands of 0.6 inch nominal diameter. That is all nicely tabulated, I think much clearer in the reorganized code in one single table, 21.2.4, which has a column, leftmost column for concrete strength, and then for that particular concrete strength, you have to know the nominal strand diameter, and knowing those, you go to the rightmost column, and that tells you your minimum spacing. So I particularly like the use of tables in the reorganized code. In conclusion, we think we've developed a very user-friendly document. Now, granted, for people like me and others in this room who've been using this code ever since it first appeared, this format, for more than 40 years, not so much. I know where all the sections are for the members that I'm designing, and others do too. So for me to use the new code, it would take some learning. But I think the great value of this reorganized code is going to be for the new designers, for the kids out of school, for the first contact with an ACI code. It's going to be much, much easier, much more user-friendly. Again, all the member requirements are in one place, and it will provide a very stable platform to accommodate future materials, future design ideas, and future design methods. Thank you very much.
Thank you, Ken. I was going to say, I wasn't sure where Ken was going with that comment about the 1910, that when he went back and was looking at what was there, I actually thought he was going to make a joke about late night TV and say that when he looked at it, that actually the great senator of Arizona, John McCain, was actually on that committee. So, but apparently that wasn't the case.
It had a lot of joke possibilities.
So we're ready for questions, both from the audience and certainly in the webinar as folks as well.
First, I'll apologize for my lack of voice. I hope you can hear me. Ken, you said that we've made liberal use of tables and figures. I agree with tables. I'm not so much in agreement with figures. Do you think maybe you or Randy or someone could comment on why we are not making more liberal use of figures?
Jim, what's wrong with your voice? I don't want to know. I'm not sure I understood.
So the question is, we have made maybe a modest increase in use of figures, but not much. We liberally are using tables and not figures as much. I think a lot of that had to do with, we discussed that. There were a number of cases where we probably could have, even a figure would have been preferred over a table. But a lot of these figures, it was interesting looking at some things like in seismic detailing or whatever, it might in the code convey that this was in fact the way it had to be done instead of the way it could be done. And so the concept of the figures made it more difficult to provide some clarity in that there was the designer could in fact do different things, whereas really what we're trying to achieve with tables are kind of minimums and maximums that have to be satisfied in the design. So yes, maybe in the future we can move more that direction, but there were a lot of cases where figures just did not seem to be appropriate. Jack, you may have had, or Ken, there were some ones that you may want to discuss.
I don't think I could have said it any better than you did, Randy, but I should have clarified that the use of figures is primarily in the commentary, not in the code.
A number of folks have mentioned some of the historical codes. For those of who might be interested, I think ACI, do they still publish there is a CD floating around somewhere that has all of the historical codes all on one CD. I think ACI still publishes that. Mike, that is the case?
Yes, it is a CD-ROM, and the title is Codes of the Last Century. So they take you from 1910 through 1999. These are.
Actually, there was a 1908 National Association of Cement Users document that I don't think was quite officially a code, but that is on that CD, and that was only 7 pages.
I suspect a lot of designers would like to have a code that isn't really a code, right?
Jack, I have a question regarding the seismic design of diaphragms. What's the aim of 318 regarding this design of diaphragms? Is it to have an elastic behavior or inelastic one? If it's the second case, it's not the same having a welded wire reinforcement or the conventional one, because the first it has a very fragile behavior as compared with conventional reinforcement. Do you have any comments?
So the question relates to design of diaphragms, and specifically seismic design of diaphragms. And as is the case with all the elements of the building, the loading side comes out of one code, and the resistance side is coming out of the ACI's 318 building code. And diaphragms have been a hot topic in recent years, mainly on the loading side, I think. The magnitude or intensity of the loads that is in current U.S. codes has been questioned by several, as a result of measurements during tests, during earthquakes, analyses, and so forth. One of the questions that's coming up, well, if the diaphragm forces are in fact many times larger than what we're designing for, maybe the performance of the diaphragms will be inelastic, whereas traditionally we've really intended that the diaphragm be a mainly linear responding element within the system. And so in Chapter 21 there are provisions that are intended to result in a diaphragm of at least modest inelastic capability, but the intent is primarily that it should stay mainly in the linear range. If a model such as the simple B model that was presented earlier is used for the design, there is a lot of reserve strength that's available in a typical diaphragm. But certainly going forward, I think there'll be room for some improvements in future codes. But the intent really is to keep the diaphragm essentially in the essentially elastic range.
This is a comment and more. I noticed that we've seen these graphs of increasing number of page numbers as the years went by, but nobody commented on the fact that there actually was 1 year that it decreased. 2005 was a bit less than in 2002, right, Jim? And I won't take credit for it as the chair of the committee, but if Sharon Wood has gotten here yet, she should take credit, because that's when we changed the notation. And actually, instead of having new notation in each chapter, we just had one chapter of notation in terms, and that reduced the code. So next time you guys do this, please notice that one little blip in the trend.
We considered that an outlier.
I think there was another year when the size went down, but that's because we made the book bigger. So instead of having the small format, we had a bigger format. So that's another way to do it.
Words per square inch.
I noticed that there is a chapter that everybody is there somebody who has a question? Okay, one chapter that was totally overlooked in the existing 2011 code and in the coming code And this is the chapter that talks about ASTMs. I think, Terry, in your presentation, you said that in the materials you are going to reference the ASTMs. And that is okay. But one thing that I feel we don't pay much attention to is the fact that you really cannot design and build by ACI unless you are dealing with materials of known properties. And by this I mean, if I take the example of the reinforcing steel, grade 60 is ASTM A615 or A706, but having grade 60 by itself is not enough, because you have to specify what is the minimum elongation, what is the minimum reduction in area, and all of this leads to ductility, and ductility is a fundamental property which we are basing our designs on, having ductility, so that we have a warning before anything happens. Now, I'm stating that because starting in the 1956 code, I think it was the first time that the ASTMs were listed with the year of their publication. And having an ASTM and the year of publication in itself is not enough, because in the early editions of the ASTM A416, the requirement for the diameter of bend was not stated in the body of the ASTM. And as a result, there was no assurance or insurance that you are getting a reinforcing bar where you can bend it according to the diameter specified in the code, 6 diameter, 8 diameter, whatever it is, without the bar cracking. So ACI 318 had to adopt ASTM with exceptions, which takes us to today's ASTMs. We still have some exceptions to the ASTM, and anytime we reference a new edition of an ASTM, we have to look at what changes were made from one edition adopted in the past to the next edition that we would like to adopt, and make sure that it is compatible with the ACI building code. So this is a comment, but
it's an important one, actually. It's essentially Chapter 3 of the code where all of those are listed. And I guess we need to give credit where credit is due, because we say we have 8 subcommittees. We actually have a 9th subcommittee that is consists of one person. That person is Dave Gustafson. Dave is very meticulous in going through a lot of these ASTM standards, and in fact identifying these changes and noting in context the appropriate exceptions and so forth. It's really a very tedious job, and we've been fortunate to have Dave and others. I know, Bazil, you active in looking at those as well, but it is a tedious job.
Tony does the same thing on the concrete.
And Tony on the concrete side. Thank you.
Since this is the last session on ACI 318.14, what is the future plans for educating the structural engineers and getting this code out so people can start using it? There's probably going to be webinars, there's probably going to be in-person education, but also are there going to be design guides or anything else produced by ACI that will be helpful for the practicing structural engineer? I don't know if you guys are the ones that answer this or somebody.
Yeah, you're probably right that that question is probably above our pay grade, as they say, and I'm not sure exactly. I know generally what has been planned, and certainly there is going to be a rollout. There certainly has been discussion of design guides, and there had been, PCA had been doing the notes. I'm not sure exactly there may be a transition with that and so forth. Okay, so you know, Mike, maybe you can address some of these ACI perspective on what's being done.
I do know that we're planning to update the reinforced concrete design manual so that it's current with the 14th edition of the code right about the time that the new code comes out.
I would just add one other thing. We're going to try something that we haven't done in the past, and that I'm a long-time speaker at World of Concrete, and so I'm going to speak at World of Concrete. basically what I talked about this morning, but a much more detailed version of it, and try and hit that audience. Charlie Dolan will be at World of Concrete to talk about the overall reorganization. So we're aiming for, as much toward the user side as we can.
I mean, related question. I haven't heard a whole lot about those that are in the writing the textbooks, exactly what their intent is. Certainly, there seems like there may be some modest changes that have to go along with that. But things. It's been a big and hard enough task concentrating on this code, particularly for those that are involved in 318, that perhaps then already be looking ahead at the textbooks.
In answer or partial answer to the question about education materials, there's a new task group on communication platforms of the future for ACI, and one of our discussions is about apps to go on your smartphone. So if you have any specific examples of apps relating to the new building code that you'd like to see, talk to David Lang, who's chair of that task group.
We have 5 more minutes to go, and you won't go to lunch unless you ask a question. I know, Ken, like you, I didn't want to reveal my age, but I have to say that Ken has been a member of the committee for the last 400 years.
450. I worked on the 1910 code.
Lo hacemos en español, entonces. One comment as my has to do with the Spanish version. The status at this point is 9 chapters have already been translated into Spanish. They have been provided by the Chilean Institute of Cement and Concrete, and we hope to finish on time. We finished it before the 11 version, so this time we try to do it again for the Spanish one to have it on time. It's arduous task, and is being done the same way that the rest of the code is done by consensus. Every translated chapter is voted on with the same rules. Negatives have to be explained, so it's exactly the same. And 2 versions are being worked. That's been done since the 11 code. One is the in SI metric units, and the other one is in U.S. customary units. That's mainly for the use within the U.S. in Puerto Rico, and most of the workers speak Spanish, so it's being used all throughout the southern states. So we hope to have that on time for the appearance of the 14 code. And maybe we could go to lunch.
I think Terry was hoping to hear that you already had Chapter 26 done in Spanish and then could simply translate it over to English for him.
If the rule is not to convince you but confuse you, probably we should do that.
As long as the mic is here, I was hoping that one of you gentlemen would mention that the reluctance to use figures in the code was due to the fact that the lawyers objected to it. But you probably don't know that, but I understand. And what Ken mentioned is that this is going to be difficult to use for old-timers. Maybe you should have 2 versions of the code and limit one with an age as to who could use what. Thank you.
What about some of the young engineers and future engineers in the audience? Do you have anybody wants to make a comment? Those of you who have been exposed to the existing code and heard what the next edition is, anybody? I'm pointing in one direction, everybody turns their head. Okay, good. We have a volunteer here.
Just a comment. It seems like you're going to do the textbook manufacturers out of business with this new code, because it seems so well organized. As a young engineer, I think it would seems like you could almost just pick up this code now and go for it without having to read a textbook. Or yeah, that's just a comment I had. Congratulations.
Hopefully we haven't got it so precise that we're putting the faculty and academics out of business. Certainly, I think the real thrust in terms of education, in my mind, it's one thing to design and you have a code that you're meeting for design, but it's another, I think, very important that you have to understand the behavior. So I think that's why I said I think really the textbooks are probably only going to have perhaps some modest changes, but the most important thing in terms of educating and learning about structural concrete design is really about the behavior. And once you understand that, then yes, I think this would be much easier to apply in design practice.
Randy, let me add to that, though. I think most of the reinforced concrete textbooks are organized already just like this code. They're about beams and they're about columns and one-way slabs and two-way slabs. So I don't see that it's going to be a big change for the textbook writers. I don't speak on behalf of all university professors and educators, but I can't wait to get my hands on this code and get it in the classroom, because it's going to be so much more sensibly organized and so much easier to teach the students. And if the old-timers have a hard time reading the new code, hire some of the new graduates.
Or make the font size bigger.
Seems like we have time for one last question or comment.
Good morning. We are from University of Costa Rica, and in my position, I'm so glad about the new presentation of the code, because in some exams or proofs or tests, we can finish the exercise because we spend a lot of time searching the equations or the comments, and it's a best improve in this time. I'm so glad about it.
Well, thank you for that. It sounds like a positive reinforcement. I forgot, how much did we say we were going to pay you for that comment?
I think the building codes will last longer because there's going to be less of this paging back and forth.
Okay. Well, I want to thank everybody for sitting patiently through this second session about the reorganized code.